Hello ladies and gentlemen, and welcome to my presentation about the topic Update on the indirect efficiency determination of permanent magnet synchronous machines. Let's have a look at the table of contents. At first, I will give an introduction about the present situation of efficiency determination methods of electrical machines. Then I will explain the novel concept of the alternative method for permanent magnet synchronous machines. Afterwards, I will show some actual measurement and simulation results, and I will finish the presentation with a short summary. So let's start with the introduction. At this slide you see an overview about the currently standardized efficiency determination methods according to IEC 60034-2. 34-2-1 and 2 address the fundamental losses of induction machines, synchronous machines and DC machines. In this presentation I will focus on synchronous machines. For electrically excited synchronous machines, several methods are included in the standards. On the one hand side, a direct efficiency determination via input and output measurement is possible. And on the other hand, there are the indirect procedures by summation of individually determined losses. The additional methods D to G, which are not compliant to national energy efficiency regulations, won't be addressed here. Also, the specific test methods according to 60034-2-2, like calorimetric efficiency determination, are not addressed. The indirect procedures B and C are used especially for large machines with a rated power of several megawatt, which have a rather high efficiency above 95%. Here a smaller measurement uncertainty can be achieved in comparison to the direct input-output measurement. If we take a closer look, we will notice that these methods are based on a separation of the machine's losses into no-load losses, load-dependent losses and excitation losses. For this determination, a variable excitation is necessary, which is obviously not possible with a fixed permanent magnet excitation. Therefore, currently the permanent magnet synchronous machine only allows the direct procedure of efficiency determination, while the other methods cannot be used. But due to the increasing number of large permanent magnet synchronous machines, an indirect procedure would be useful as well. As permanent magnet synchronous machines are usually operated at converter fed drives, additional losses due to current harmonics occur. IEC 60034-2-3 describes the determination of these losses by comparing sinusoidal and converter operation. We will discuss these losses later again. So we can summarize that the indirect efficiency determination methods are state-of-the-art for large electrical machines with high efficiency values above 95% due to the lower measurement uncertainty. But currently only the direct determination is standardized for permanent magnet synchronous machines. Therefore, we proposed an alternative indirect method in the year 2014. Since then, this method has been evaluated on different permanent magnet machines with a rated power up to 150 kW at our institute and on one smaller machine at the PTB, this is the National Metrology Institute of Germany. Here you may find the list of the relevant publications. The upper part is related to our institute and the lower part is related to the PTB. I will show some of these results later. Now I want to give an overview of the alternative method and the used assumptions. If we take a look at the equivalent circuit per phase of a permanent magnet synchronous machine with the stator terminals at the left, indicated by the stator voltage US and the stator current IS, then the synchronous reactance as sum of the main and the leakage reactance, and the synchronous back EMF UP at the right. Then we notice two resistances, the stator resistance Rs plus delta Rs and the equivalent iron resistance RFE, which are indicating the main loss components. Please keep in mind the induced voltage Ux, which is proportional to the magnetic flux density and drops over the equivalent iron resistance. Now we want to separate the losses similar to the electrically excited synchronous machines. So we have the voltage depending losses, which are mainly iron losses that are determined during a no-load test at variable speed and then recalculated with help of the voltage Ux square, as the iron losses depend on the square of the magnetic flux density. Like already mentioned, the harmonics due to converter feeding lead to additional losses. In our case, these losses are determined by comparing the fundamental and the total input power at no-load operation with help of a polyphase power analyzer. Then we have the current-depending losses, which are classical I square R losses in the stator winding and additional stator losses, which is indicated by this delta Rs. They are determined at sinusoidal feeding of the stator when the rotor is removed. Due to that procedure, no additional rotor side losses can be considered. The third component are the mechanical, friction and windage losses. They occur already at no load. In order to perform an accurate recalculation of the iron losses, the mechanical losses are either measured with a non-magnetized rotor or calculated, if this is not possible. This diagram symbolizes the process, starting from the no-load and the removed rotor test, over calculating the losses at load, that means the current-depending losses that are proportional to Is square, and the load-dependent iron losses that are proportional to Ux square, and the mechanical losses. Then we come to the indirect efficiency at fundamental operation. If the additional losses of the converter feeding are taken into account, then we get the indirect efficiency at converter operation at the lower right side. This procedure is currently under review at the IEC Working Group 28 for inclusion in the 60034-2 standards. So, what are the main assumptions of the method? First, the dependency of the iron losses on the square of the induced voltage Ux. That means on the square of the magnetic flux density. If we, for example, measure the no-load losses PFE0 by subtracting the friction and windage losses from the total losses at no load, the iron losses at load are calculated according to the given formula with the induced voltage Ux and the no-load voltage U0. Secondly, we assume that the additional rotor side losses are small, which holds true for machines with integer slot distributed winding. And at last, the additional losses due to converter feeding are assumed to be nearly load independent. This is valid especially for machines that have a linear torque current curve. Then these losses can easily be added to the total losses as a dependence of the modulation degree of the converter. That means dependence of the stator voltage. Now let's continue with the measurement results. Here 4 permanent magnet test machines are shown. The two at the left have a tooth coil fractional slot winding. The lower one has one subharmonic stator field wave. The other two machines have a distributed single-layer integer slot winding. One machine with a shaft-mounted fan and the other one with an external fan. These external fan losses will not be considered in the following results. As I said, one main assumption is the dependence of the ion losses on the square of the induced voltage Ux. This is compared here for all four machines. The losses A, as written on the left side, are calculated from the simulated no-load losses with help of the voltage Ux and the no-load voltage U0. And then we have the losses B that are taken directly from the load simulation values. You see that for the test machines 1 and 4, a rather good accordance is achieved at rated speed, while for machines 2 and 3 the losses are overestimated up to 25%. If we now calculate the efficiency from the simulated values in two ways, that means directly from the load simulations and indirectly according to the presented method, then we see a good accordance for test machine 4 here at the left side. Also, the comparison of the measured direct and indirect efficiency values at the right hand side shows a good accordance if the error tolerances due to the measurement uncertainty are considered. For this machine, the calculated air friction losses are very small. Due to the limitations of the converter of test machine 3, this machine could only be operated at half the rated speed. But, like before, a good accordance is visible. The friction and windage losses of this machine are much higher than before. As no-load test with unmagnetized rotor was possible, the losses were calculated with the given formula, where RRO is the outer rotor radius and LFE is the active ion length. Now I come to the smaller test machine with distributed winding and surface-mounted rotor magnets, which was evaluated at the PTB. Here also a very good accordance between the measured indirect and direct efficiency is visible. So if you look at the blue and the gray curves. The yellow and orange curves shows the amount of measurement uncertainty. Here also the uncertainty is lower for the indirect procedure. For this machine, the friction and windage losses were measured separately with a non-magnetized rotor. At last, here's the comparison for the both tooth coil winding machines. For test machine 1, a rather good accordance during simulation and an acceptable accordance during measurement, the lower side, is achieved. Test machine 2 with the subharmonic state of field wave on the right hand side shows a bigger deviation, so we see up to 1 percentage point deviation at rated operation. And also the deviations at measurement are higher. So finally we come to the summary. I presented an alternative concept for indirect efficiency determination of permanent magnet synchronous machines, which has been evaluated by measurement and simulation and is now at a review stage for inclusion into the IEC standard. We saw a good accordance for machines with distributed winding and an acceptable accordance for special machines with fractional slot winding. So, thank you for your attention.